Okay, so here's the second video for the statistics review, covering questions 4 and 5. I've gone ahead and done a little bit of the graphing ahead of the video so you don't have to watch me plot points and all that. So this might go quickly, but you're welcome to pause if you're writing out your own note and plot the points carefully yourself. So this question says that water was boiled and then allowed to cool. The temperature of the water was recorded every minute once the water was removed from the heat source. So we're watching it cool. Construct a graph of this data. So there's a great big data set on the right side there with time given in minutes and temperature in degrees Celsius. It says it was removed, the water was removed once it started to boil. So there's the 100 degrees at the zero, the beginning time. And then a measurement was made every minute, recording the time in degrees Celsius. And this was done for 30 minutes. So that's a great big table of values, a lot of points to plot, just to be aware of. So the first thing I've done here is choose my dependent and independent variable. I believe that the temperature of the water depends on how much time has passed since it was removed. So remember, dependent goes on the y-axis and independent goes on the x-axis. So the one that is like changing and causing an effect goes on the bottom, and the thing that's changing as a result of the other variable is the y-axis. Okay, so I've also added a scale. There's some tick marks every other grid line. I didn't label every one of those just because it gets busy, but each one is going to be worth 10. And then I've chosen to label every other one, just the even, or just the, like the 20, 40, 60, counting upward. So each, there is 10, and the individual grid is going to be a 5. If you wanted to break it down like all the way, each line is worth 5. On the other axis, the tick marks I've set to be worth 2, 2 minutes. And that means the individual grid lines in between them are each worth 1. So 1, 2, 3, 4, 5, 6 minutes, and that fits all the way out to 30. I didn't label everyone, I was a little bit lazy. All right, so you're going to be plotting those points by hand. You can pause and do that right away. I'll flip and show you mine in a second. But the first thing we're going to be adding to that for question A is a line of best fit. All right, so I went ahead and plotted those points. They're not perfect. It's a very faint grid on my screen here. But our data starts at 100 degrees Celsius at time 0, and then is going down, 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 down. You can just check out that one of the points makes sense. After 7 minutes, the temperature should be 80. 7 minutes, the temperature should be 80. After 17 minutes, the temperature should be 65. 17 minutes, the temperature should be 65. So double check that I've done an okay job of plotting those points. They're not perfect, of course. Plotting to the nearest tenth of a degree Celsius on this grid is not easy to do. So I've plotted the points. Next job is to make a line of best fit. So I added that. You'll notice maybe that the data points are above the line of best fit at the beginning, and they're also above the line of best fit at the end. That's a clue that maybe linear is not great, maybe quadratic, which seems a little bit silly because the temperature is not going to rise again. Or this could be exponential. So maybe it's cooling quickly at first and then more gradually as time goes on, like leveling off at some temperature. So maybe exponential would be a better choice, but this one says to make a line of best fit, so that's what I've done here. Next up, it says, is this linear, quadratic, or exponential? So I don't think linear is the best fit. I'm going to guess exponential. Because it's slightly curved. I don't believe that it's quadratic, as I said, because I don't expect the temperatures to start rising again while this water is off of the heat source. So I think it is probably going to level off as it gets close to room temperature or some other temperature. So that's partly from the graph, and it's also partly from my own life experience. All right, so next up, the question B. Oh, I've added a Desmos graph. I'll come back to that one in a second. The next question says perform a linear and an exponential regression and record the equations here. So I've done my own hand-drawn graph. I made my own hand-drawn line of best fit. It's probably not the best fit. So Desmos is the best way to do that. Or if we were in person, then a graphing calculator. So I'm going to flip back and show you my Desmos version of that graph. I added axis labels, which you can do in Desmos using the little wrench. You can type in axis labels. Kind of a cool feature. You can also zoom in or out however you like, or use that zoom fit button that was on the far left of the Desmos website. After you finish typing in your table of values, there's a little magnifying glass, and if you hover over it, it says zoom fit, and it makes all the points fit nicely in your space on your screen. So there is the same set of points. In black, there's a linear fit, a straight line, and in blue, there's the exponential fit. So it's a pretty gradual curve, but blue is curved. You can tell because the ends are higher than the center. So it does have a slight upward curve. And from these, I can grab the parameters, is what that Desmos is calling them, the A and the B values for my linear and exponential fits. Okay, and then the straight line is going to have a y equals ax plus b or mx plus b format, and the exponential looks like this one, a power with a multiplication factor in the front. So I'm going to go and add those two equations to my slide. The linear one is negative 1.48 times x plus 92.13, negative 1.4, oh, maybe it should have been 9, just to be precise, negative 1.49 x plus 92.13. And then the exponential fit, the A value that goes in the front is going to be 95.06, and the base is 0.98. Oh, keep picking the wrong way to scroll. 95.06, and the base was 0.98 or 978 if you want to keep a little bit more precision. Okay, so a linear model and an exponential model. Which line, or you can change this to say which fit, since exponential is not a line, which fit has the stronger correlation? So I'm going to head back to the Desmos screenshot and look at the R-squared values. So the R-squared value for the straight line is 0.9605. And then I'll look up the exponential one. .9852. So the exponential one has a slightly higher number, a little bit closer to 1. So this is the better fit. Therefore, it has a stronger correlation. That means the points fall closer to that line. They fall closer to the blue line on average than the black line. So that's what that R-squared number is telling us. All right, the last question for this This scenario here says use your equation to predict when the water will reach room temperature. So when is it going to be 20 degrees Celsius? Is this interpolation or extrapolation? So extrapolation, remember this goes beyond or outside of the known data. And interpolation is between known data points. So it's like in between known data points. Okay, so it says use your equation. I just decided that exponential was the better one, so we're going to be using the exponential equation. I'm just copying it down. And in this equation, we start out with two variables, but here in the text of the question is told to me that the temperature is going to be 20 degrees. Remembering my graph, I've had temperature on the x-axis. So, sorry, time is on my x-axis and temperature is on the y-axis. So when the question tells me a temperature, it's giving me a value to plug in for y. So I'm going to replace y with 20 degrees. To solve for x, we haven't actually solved this type of equation, but we have most of the tools for this job. So I'm going to divide both sides by 95.06 to get rid of that multiplier out front. The answer to 20 divided by 95.06 is 0.2104. And then I'll copy what's left over on the right side. And this is where we haven't actually tried this type of question before. We don't yet have a strategy for solving for x. However, if I think about what this equation is telling me to do, it says multiply 0.978 by itself many, many, many times. That's what an exponent does. So if this was a 2, I would multiply the base by itself twice. If it was a 3, I would multiply the base by itself 3 times. If the exponent was 100, I would multiply this number by itself 100 times. So what we're looking for is what's the magic answer for that exponent so that the final answer pops out as 0.2104. So using a little bit of, I don't know, detective work, I see that we got our temperature down to 50 degrees after 30 minutes. So I'm not going to waste my time like thinking about these times. I know the temperature is not 20. So I'm going to jump down to maybe 50 minutes and see when I plug in x equals 50, see if my temperature is low enough or if I have to go even farther than that. So a little bit of guess and check or trial and error. So I'll just show a couple of them. So 0.978 raised to the exponent 50 gives me an answer of 0.3288. That's too big. So I haven't brought my curve down low enough yet. So I need this number to, my answer to be smaller. So I'm going to multiply by a fraction more times. So I'm going to do an even bigger exponent, more time passing. I'm going to try out 60. And that brings my decimal answer to 0.2632. If I go even farther to bring that number down a little bit smaller, 0.978 to the exponent 70. Oh, that's pretty close. That's 0.2107. So just like a hair too high. I'll make a really small change to 71. And that brings the decimal to 0.2061. So I went too far. So this is my best answer. So around 70 minutes. It takes approximately 70 minutes for the water, temperature, to reach 20 degrees Celsius. 20 degrees is 70 minutes and 20 degrees are way past what was originally graphed. This is extrapolation. Because it goes beyond the known points. And there is one more way we could try doing this. This is a little bit of work to guess and check. Like if your first guess is way off, it takes a long time to narrow down to the right exponent value. But another thing we could do is make use of our graph. So the hand-drawn graph, not so much, but the Desmos one, you have the power to like click and drag the screen anywhere you want. So you could drag it forward. So you can see the time of see a temperature hitting 20 degrees. And that's where you're going to notice the time. So we want to find where this curve has a temperature of 20 degrees Celsius, and we would read the time off that corresponds with that. So we can like drag the screen. This is just a screenshot of it, so I can't actually do it, but you could use your Desmos graph to find that answer as well. So you'd be looking for 20 degrees and reading the temperature that corresponds with that. All right, so there is a big graphing example. We've got one more short question that we're going to do that falls within the statistics kind of theme. And I've forgotten to put the screenshot in here. Bear with me for just a second. Okay. So this last page of the review package looks at sampling techniques and sampling bias. This is a lesson that you did like watching a video on a day that I was away. So hopefully you actually did that and this isn't the first time you're seeing it, but just in case, I am going to go through it with you. And I'm going to add those last questions up. Okay, so which type of sampling is used in each of these scenarios? There were five sampling techniques that were discussed in your note. This is simple, random sample, voluntary samples, convenience, cluster, and stratified. Sorry, stratified. And there's definitions for those. I think that was cycle 3, day 3. If you want to look back at the full note or the video lesson that goes into detail on this stuff. But which sampling technique is used in each? So the first scenario, 6 baseball teams from a league are selected for a survey. So full teams have been chosen. You could think that maybe that is simple, but there is some like structure to it. So there's a cluster of people that have been surveyed, like not the full baseball league, just a couple of teams. So groups of people within the baseball population. So cluster is probably the best answer for that one. The next scenario says an internet site requests people send emails stating their opinion on the latest political platform. Since this is like online, they're asking you to send an email. Nobody has to do that, and most people won't do that. So this is a voluntary survey. You choose if you want to send in a response or not. So that would be voluntary. And then the last one here, a marketing company randomly selects people to participate in a survey such that the number of people in each income group is proportional to the size of the groups. So this one has a couple of keywords in there. Really proportional is an important one. So they're picking people for the different income groups or levels, and they want their survey to be like following the right proportions. This is the stratified survey where you've broken people into groups or the population into groups first based on some criteria, in this case income level, and then you're going to pick maybe like 1% from each group or 10 people from each group. So you can do that a couple different ways. But this has the idea that you're splitting based on some criteria first. All right, so the other ones that were not used there are the simple random sample, which is like drawing a name from hats. So totally simple, everyone is equally likely. And the other one that wasn't used, oh, what did I miss? Simple, oh, convenience. A convenience survey. This is like leaving a little paper slip at the cash register and hoping somebody fills it in. Or asking people that walk through the door of your store. That's pretty easy to do. Okay, so there's two others. There's 5 in total, different ways of sampling. All right, next question, number 6. When talk show radio hosts ask their listeners to call in and give their opinions on the upcoming election, statisticians consider this to be sampling bias. Why? So how is there potential for bias in this type of survey? So they're asking people to phone in, so that's voluntary. Nobody has to phone the radio show. So it's a voluntary survey, and the question here is, why would a statistician consider this to be sampling bias? So in this scenario, people volunteer to call in. They don't have to. And usually it is people who have strong opinions one way or another that choose to phone in. So they're really, really, really strongly in favor of a certain politician, or they're really, really, really against one. Anyway, so like the polarized, like strong opinions tend to be the ones that phone in. If you are like a more moderate person, you don't have really strong opinions, you're maybe on the fence between the option, like the different options, you would likely not call in. So the people who phone are likely to have very strong opinions one way or another. So not the moderate thinkers. So that kind of middle group of the population wouldn't be heard in this survey. Their voices would be left out. All right, last 2 questions, and they're also about bias. So number 7 says, a survey question stated, the current government is promising to put money into creating jobs. Do you think they should be re-elected? Rewrite the survey question so it does not contain response bias. So the way it's written right now, well, let me grab a highlighter. There is definitely chance for bias. The current government is promising to put money into creating jobs. So the way this question is asked, that's like thrown into your head as like the thing to think about. You're thinking about creating jobs, and maybe you don't have a job or you've lost your job, and this is really, really appealing. So there's a chunk of the population who this little intro sentence would really like connect strongly with. A chance to have bias there. If we ask this question in a different way, maybe a more simple way, do you think the current government should be re-elected? You're leaving it a little bit more open for people to think about whatever they think is important in making that decision, instead of like implanting this job creation factor as the most important one in their heads. So just leaving it a little bit more open, not so like leading you towards a certain answer. So the problem is the idea that's being placed in your head um, with the extra sentence at the beginning. Okay, number 8. Is there bias in the following scenario? Explain. A survey asked, should all students be required to write standardized tests to graduate from high school? In which subjects? So the survey is about standardized tests. It said, should all students be required to write them to graduate from high school? In which subjects? So there's a lot of stuff going on in that question. And it says, is there any bias? So most of the time there is a chance for bias. In survey questions, it's really tricky to write a bias-free survey, usually because you have an outcome in mind when you create your survey, so it's hard to not lead people down a certain path. But in this case, people who tend to do well or have done well on standardized tests or with testing will likely say yes. There's also some bias in this question in the assumption that people, like all students, are going to graduate from high school, and some will not for many reasons. So there's some assumption built into it. So most will graduate from high school, but not all. And in which subjects? There's not really bias in that. It's left open. It doesn't say should all students be required to write standardized tests in math or in language or in like any specific area. So this is open-ended. So okay. So that last part doesn't really have bias in it. One thing that I'm curious about in this question that is not made clear is who is this survey being given to? Is it being given to the high school students? Is it being given to all high school students? Is it being given to the whole population? So depending on who the audience is, you might notice more or less bias in a given question. So that's where I'm going to wrap up. That's statistics, video number 2. And tomorrow we will do our last 2 review topics, some algebra stuff and finance.